Hi, everyone. Thank you for joining us today in the Statistics and Data Science webinar. It is an 8-part webinar series. If you haven't already, please download the slides through the link that has been shared by Sahana in the chat. So we kickstarted the Statistics and Data Science webinar series last week with exploratory data analysis with Jane. Today we will be talking about data and sampling distribution, which is an important segue into statistical experiments. If you're new to data science, statistical experiments is as important a topic as machine learning models. And with that, we will advance to different machine learning models and like classification and supervised machine learning models towards the end of the webinar series. So we will have one each webinar on every Saturday at 12 p.m. ET. Thank you for joining us today. Let's begin. Before we start that, thank you to all our volunteers. Today in this call, this is me, Sneha. We have Rishika, Aryan, Arushi, and Sahana today with us. They will be taking care of the Zoom chat and Q&A session. Rishika and Ravi will be taking the middle part of Q&A where they will answer all your questions. So looking forward to that. Next, a huge shout out to our sponsor, the Home Depot. They have been very supportive, and the next thank you is to all of your feedback from the first webinar. We really appreciate that. We also have a survey towards the end of this webinar. Please make sure you take a minute to answer the questions in there. So for today's session, we have a very awesome notebook on data and sampling distributions. We are covering a wide range of topics, from random sampling and bias to central limit theorem and confidence intervals and the various distributions that you can expect in data. And our speaker today is Ravi Bansal. I'm super glad for Ravi to make time for us. He is a graduate in textile engineering, and he is a self-taught programmer, and he's currently working as a software engineer. He started dabbling into AI and Python for a while now, and I would say he is a very much an expert in Python, and I'm super glad to have you here, Ravi. Thank you. And before we start our session, just want to say that we have simplified how we open our Google Colab notebooks. All you have to do this time is just to click on this link to open the notebook itself. So if you have downloaded the slides, you would have this link. Sahana will also share the link to Google Colab on the chat. So all you have to do is click on this link to open the Google Colab notebook. It should load in about a minute or two. Please give a thumbs up if you have followed so far and have opened the Google Colab notebook. Awesome. I would request you all to just follow along with the notebook without running the notebook itself. Ravi will share towards the end the notebook along with the data. Then you can actually experiment once the webinar is over. Thank you, and over to you, Ravi.
Sneha, can you just confirm if I'm audible?
Yes, you are.
Is my screen visible?
Yes, it is.
So I think we are good to start then. So thanks, Sneha, for the introduction, and I'd also like to thank WWCode for organizing this amazing 8-part webinar on these amazing topics, and also all the volunteers for helping and organizing. So it's good to see people from all around the world joining it. So I think we can start now.
Yes, you can.
Okay. So first we'll have a look at like what statistics is and why it's so important. So okay. So Coming to the definition of statistics, so the best definition I found is defined by Croxton and Cowden, and they define statistics as the science which deals with the collection, analysis, and interpretation of numerical data. So basically, statistics is all related to all the operations that are related to numerical data and its analysis. So why study statistics? Like why data scientists and machine learning engineers need to know about statistics? And I found this really funny memes which do a good job in explaining why it's important, because a lot, or I'd say almost all machine learning and deep learning algorithms are basically statistical pattern recognition. So that is why statistics is at the background of both AI and machine learning. So we'll start with what the one of the key and central concept of statistics after the central tendency, that is probability distributions or the data distribution that people generally like to call. So what is a probability distribution? So before that, we need to understand what is a random variable. So a random variable is just a mathematical function that assigns a numerical value to each possible outcome of an experiment. That is, it maps real life events to numerical values. For example, a coin toss. So we all know that there are two outcomes when a coin is tossed, that is a head and a tail. So if we can denote these outcomes with a number, say I would say head with a +1 and tail with -1 or 0, or you can take any values that you want. So this is a random variable that maps the events head and tail to a numerical value that is +1, -1, or +1 or 0. So then comes the concept of a distribution function. A distribution function is a mathematical encoding of probability laws of all the events in the experiment. So basically it defines what is the chance of each of the event happening in an experiment. Again, if we go back to our coin toss example, like we all know that in a fair coin there is a 50-50 chance of both head and tail. So this is its distribution function. So there are two types of distribution functions, that is a discrete one and the continuous one. So both are distribution function and they both define probability. The only difference is that for a discrete probability distribution, the values of a random variable are discrete, just like in a coin toss, head or tail, or in a throw of a die, 1, 2, 3, 4, 5, 6 are our outcomes. But in a continuous probability distribution, the variable can take any real number value. For example, if you are measuring height of a group of individuals, so height can be any real number between a certain range. So then we have a continuous distribution. So, in a nutshell, we have an experiment and a random variable maps the events of the experiment to to a real value, and a distribution function maps that real value to the probability of that event. So there are certain important distributions that every data scientist and every statistician should know. And first of all is binomial distribution. So what is a binomial distribution? First of all, it's a discrete probability distribution. And what it does is a random variable. A random variable is just a variable which describes the outcomes of an experiment. It can be like if you are asking the question whether there will be rain today or not, or what will be the score of a football match or a cricket match. So anything is a random variable. So a binomial distribution is one which assumes that our random variable takes all positive values and the probability mass function is given by this. So basically, in a binomial distribution, the probability function or the mathematical law of probability is defined by this formula. So basically, every different distribution has a predefined uh, probability formula that the mathematicians have always figured out. And why we are studying these is because they helps to analyze data. Like if we know that our variable is following binomial distribution or any other distribution that we see on data, So we can easily figure out a lot of things about the data. So we'll come back to this formula a bit in a detail, like what it is and how it works. So first important thing about binomial is the experimental conditions for binomial distribution. So binomial distribution is very simple to understand, and it can be applied in a specific case where the result of your outcome is binary, that is a success or a failure. Just like toss of a coin, we have only two outcomes, that is a head or a tail, or a toss of a match, that is a win or a lose. So the result should be a binary outcome. And the each of the trial, what do I mean by trial is a repeated extension or repeated occurrence of the experiment. Like if I'm tossing 10 coins, I'll say I'm having 10 trials of a coin toss. So each trial should be independent of each other, and we know that each trial is independent of each other, and the probability of success is constant. Like every time you toss a coin, the probability of head or tail does not change. So this is what this formula says, that if you have such a scenario, then you can easily figure out like what is the probability of success. Say I want to know, if I toss 10 coins, then what is the probability of having 7 heads. So I can put the values in this formula. We'll also see a Python implementation of this very soon. And I can easily figure out like what is the chance that out of 10 coins, 7 will land up head. So coming to the Python distribution, because I think for most of the people, it will be easier to understand through Python rather than through the mathematical formula. So basically what I'm doing is I am simulating a toss of 10 coins 1,000 times. So basically it's a simulated die. There is no real dice. It's just in programming. So we are tossing 10 coins 1,000 times. And we have considered it's a biased coin where the probability of head is zero point 0.7. It's not zero point 0.5. It's not a fair coin. It's an unfair coin. And n is number of trials, that is number of coins. And capital N is how many times we are repeating the experiment, that is 1,000 times. So if I run this code and I count like how many times I got head, so we can see that this is obviously like it's Python generated data, so it will be random. So the number of times you run this notebook, you'll get different result, but the basic probability distribution is the same. So you can see that number of times 0 coins landed head is 0. It can be 1 or 2, but it will be very few. And then number of times 1 coin landed with head up is also 0. So you can see that as I go down the list, the number increases, and that's because there is zero point 0.7. So per coin there is a 70% chance that head will come up. So definitely more and more coins will land heads. So this is a typical scenario where a binomial distribution can be applied, where you have only two outcomes, that is a success and a failure. So if I plot the result, so this is how our binomial distribution looks like in the graph. So as you can see that since the probability of head is on the higher side, so more and more coins will land up head rather than landing up the tails. So what I would suggest to all the people attending here is that don't go too much into details of the code. Like it's not very advanced or something that is very high level. It's simple Python, but try to understand and learn the concept first. Then you'll automatically able to understand the code. But it's better way to understand rather than understanding the code first and then getting the concept. So and anyways this notebook will be there with you people, so you can later on play with the code. I'll encourage you to try changing these values, all these parameters p and then capital N you can change and try to run again. Every time you'll see a different results, but the basic distribution should look something like this. So this is our binomial distribution. And the key takeaway is that binomial distribution tells the probability of how often there will be a success in n independent events where you only have two possible outcomes. So just to remember, a typical problem where binomial distribution can be applied is that you are doing a task n times and how many times you can expect a success. So binomial distribution can tell you the probability of that. Okay, coming to the next distribution, this is Poisson distribution. It is also a discrete distribution and also a very, very important distribution. And this is the probability mass function for Poisson distribution. What it's actually doing, we'll come back to it later. So first of all, we should understand like when we can apply this and why do we need this distribution. So it's a bit different from binomial distribution, and this first point clearly tells us what's the difference with binomial distribution. So Poisson distribution, the rule of thumb is that you apply Poisson distribution where the event that you are looking for is very, very rare, and it can occur at any point of time. Basically, like if you are studying the data of number of road accidents in a particular city, so generally it's towards the lower end of a number, but it can happen at any time of the day. So in such experiments you can use Poisson distribution where the event that you are looking for is a bit rare and it can happen at pretty much any time. So here are a few. Okay, I'll have them below. Okay, a few cases where it's applied is like number of deaths due to a certain disease. It should not be a pandemic, but due to some other disease, or chances of a radioactive decay. So these are applications where this Poisson distribution can be applied. So what it tells is this is the formula for the probability that you are looking for, and lambda is the mean of the distribution, that is average number of occurrences. Like how it works, it will be clear when we'll have a look at the code. So okay, we'll jump to the code straight away. So basically, to understand this concept, like I have taken an example so that we can understand Poisson distribution in a better way. So the problem statement is, in a book of 520 pages, there are 390 typographical errors. Assuming Poisson law for number of errors, so you can see that in a book of 520 pages, there are only 390 errors. So since the event is very rare, we can model it with the Poisson distribution. So what we are looking for is the probability that a random sample of 5 pages will contain no error. Okay, so we'll see that how we can implement it in the code. Okay, so here we start. So I have broken down the problems in a detail so that we can better understand it. So the event of interest is the occurrence of typing mistake that we are looking for, and the interval of interest is the entire book of 520 pages. So as I talked about earlier, the important parameter of this distribution is lambda, that is mean. So how do we calculate mean? It's obviously the total divided by the number of occurrences. So the average number of errors per page is 390 by 520, it's 0.75. And what we are looking for is number of occurrences of interest is 0. We are looking for 5 pages having no errors. Like what's the chance of 5 pages having 0 errors? So let's see how we can calculate that. So this is the function calculate Poisson that I have defined above. What it does is it takes lambda, that is mean of the Poisson distribution, and x, the value that are looking for, and it returns you the probability, like how likely that event is to occur. So the formula that I have shown above, this formula, e raised to power minus lambda, lambda raised to x by x factorial, I have just implemented this formula in terms of Python. So again, I'll say that there is no need to go into details of how the code works. First, try to understand the concept, and then you will be easily able to understand like how the code is written. So it's just this formula that has been encoded in Python, and it will return you the probability for any value of x. So since we are looking for 0 errors, I'll have my value x as 0, and my mean as 0.75, and the probability I get is it's 0.47. So it's a probability that that if you randomly pull out a page of that book, it has a 47% chance of having no error. Now what we want is we want a random sample of 5 pages to don't have any errors, like consecutive 5 pages. So since each page is independent of the other, because printing on one page is definitely independent of printing on another page, so basically it's a case of independent events. And I think in the previous webinar Jean talked about it in a lot more detail what independent events are. And if the events are independent, we can just multiply their probabilities. So for a single page there is a 47% chance of independence of, sorry, of zero errors. So for 5 pages we'll have this value multiplied 5 times, and we'll get just a 2% chance that there are 5 pages that have zero errors. And that makes sense because the average says that there is 0.75 errors per page. So if we multiply this by 5, we'll also look at it in Python. So if we multiply it by 5, it says that on an average, we should have 3 errors per 5 pages. But we are looking for 0 errors per 5 pages. So this event is rare, and obviously will have a very low probability, that is 2%. So this key takeaway talks about exactly this, that on an average it should be 3.75 mistakes per 5 page, but now we are asking for zero mistakes for a trial of 5 pages. So obviously the probability is going to be on a lower side. Now I have also plotted the Poisson distribution. So again, I am plotting the same data. So my mean is 0.75, size is 520, and using this inbuilt Python function. So for each distribution, you have inbuilt Python functions. So I'm using the Poisson function and I'm generating variables that are distributed through Poisson distribution. And if I plot them, the results look like this. So I would say there is no exact graph for a Poisson distribution. Like the more number of times you generate the data and you plot, you'll see different graphs, but you can expect this. And how to interpret this graph is basically you can remember that our mean was, okay, I'll go back. Our mean was 0.75. That means per page there is 75% chance of having an error. So that is why you can say that close to 0 and 1 the bars are a bit higher, but as you go to 5 6 the bars they tend to die down, and it tells that the chance of having 0 or 1 mistake per page is on a higher side, but the chances of having 3 4 or 5 mistakes in a single page is on the lower side. So it's pretty much in sync with the data and our problem statement. So after this, I'm again like I'm going into a bit more detail. So basically what I have done is from this Python generated data, I have distributed it into categories, like how many pages are having zero mistakes, how many are one mistake. So you can see the data here. So according to Python, like the data Python randomly generated from a Poisson distribution, it found that there should be around 244 pages that should have zero mistakes, 189 pages having one mistake. And this, the second cell, it has data generated from the mathematical formula. And you can found that it says that 245.63, because it's a mathematical formula, so it's bound to give in fractions. So around 245 pages should have zero mistakes. So you can see that both this data are pretty much in synchronization with each other, and this verifies our probability distribution though. So basically in a nutshell, what it's doing is that the Poisson distribution describes probability of occurrence of events in an interval of time. So here you are not interested in failure, you are interested only in the success of the event that you want and how often does it happens. So Moving forward, now comes I think the most important distribution in all of statistics and data science, that is Gaussian distribution. So a random variable is said to follow a Gaussian distribution if its probability density function is given by this formula right there. So the important takeaways from this is that whenever we talk of a Gaussian distribution, we talk of two parameters, that is mu, mean of the data. We all pretty much know what a mean of data is. And the second important parameter is the variance. So variance is denoted by sigma square, and it's the square of standard deviation. So if you have standard deviation of a data, you can square it to get the variance. Why this is important, we'll have a look at it. First we can have a look at its graph. So normal distribution has a pretty well defined graph, and if it's a standard normal distribution, it will be, the graph should look like this. And it's very famously known as a bell shaped curve because the graph clearly resembles the shape of a bell. So it's also known as normal distribution. And the important thing to note about this is that the top of the bell, this part right there, is directly above the mean mu. So wherever your mean is on the x-axis, your top of the bell will be right above the mean. So what we are doing is, we are taking our data points, we are plotting them on the x-axis, and we are measuring their probability and plotting on the y-axis. So when we do that, we find a graph like this for normal distribution. So if, and in a lot of practical cases, we find our data to be normally distributed. So what happens is that you can see that a lot of data, so basically the height corresponds to the probability of that value. So it clearly indicates that a major chunk or a major proportion of data is around the mean. So you can see that as you get closer to the mean from both the sides, the height of the graph increases or the probability of the graph increases, which tells that major amount of data is distributed around the mean. And if you go far from the mean, you almost get pretty much no data. And it's obviously clear that it's a continuous distribution because you have values everywhere on the x-axis. You do not have any discrete values. Now comes the very important question, is that why it is so special, or why normal distribution is the most used distribution in data science and pretty much everywhere. It's because the area property of the bell-shaped curve forms basis of large sample testing. So this normal distribution has a very nice area property assigned to it, and you can see it right there. So this is your mean, and this is your mean plus standard deviation and mean minus standard deviation. So if you go one standard deviation left and right from the mean, you have around 68.26% data in this range. So if you found your data to be following normal distribution, so and say you are analyzing a data, pretty much any data, say a score of a player or something like that, and if you find that, okay, my data is following a normal distribution and the mean of distribution is 10, that means my mu is 10, and standard deviation is 2, that means my sigma is 2. So what you can be pretty sure of that is that between 10 minus 2, that is 8, and between 10 plus 2, that is 12, you'll have 68.26%, that is 68.2% scores of the players will be in the range of 8 to 12. So similarly, for all different slabs, we have nice area property that we can pretty much use. So we'll have a look at Python implementation. So again, I'm using a predefined Python function from NumPy library, which will generate a data that is normally distributed. So again, it's a randomly generated data. So every time you run the notebook, you'll see a different results, and you can see that this graph is not perfect. Like if I go here, it's a almost a perfect curve, it should be perfectly symmetrical, but the graph Python generated, it's not symmetrical, and it's the reason that it samples from a normal distribution. So some values are bound to go up and down and graph won't be smooth, but more or less it is a normal distribution. So you can see that the mean that I have taken is 5 and sigma is 1. So I have just printed like I have generated 1000 values, but I have just printed 10 values. So you can see that more or less the values are close to 5 and within the range of 6 and 7. That is our sigma is 1. So 5 minus 1 is 4 and 5 minus 1, 5 plus 1 is 6. So much of the data lies in this range. It's close to 6 4 5 6 4 5, and it pretty much like it explains this like the major chunk of data should be in this region. And this is the beauty of this bell-shaped curve, that it will always happen. If a data is normally distributed, you'll always have points that are in this range, that are maximum in this range. So now comes a very important question is, okay, so it's a data distribution. We have our data, we have a distribution, but where is the probability, or how do we measure a probability? Because it's a continuous distribution, and in continuous distribution it's a bit different from discrete, where you cannot calculate probability at a point. Like in binomial and poisson, we were asking the question, okay, what is the chance for 10 heads, what is the chance for 20 heads, or what is the chance for 0 errors or 5 errors or 2 errors. But we cannot do that in a continuous distribution, and the reason is because it takes all possible values on a real number line. So basically we'll have to talk about in terms of area, and we cannot take a probability at a point. It would be simply zero, and we'll also see why it's zero. So in case of a continuous distribution, and especially normal distribution, there is a special way to calculate probability, and that is the integration. So integration is basically a technique from calculus that can find the area under the curve. So we won't have any time to like go into the details of the integration, like how it works. And you can obviously always search on internet. There is a lot of stuff like how to calculate integrals and everything. So the key takeaway is that in continuous distributions we can always talk about probability in a range. Like we can always talk about probability, what's the probability of uh, scores of a player lying between 5 and 10, 10 and 100, 20 and 30, in a range. We cannot talk about probability at a point because it will always be zero, and we'll also see mathematically why it's zero. So this picture pretty much describes how probability will be calculated. So basically what we are looking for is the chance that your variable has a value less than b. So you picked a number, say 10 or 100, and you want probability that okay, x is less than 10. So that probability is given by this complete blue shaded area under this normal distribution, and it is calculated by this integral. So below this is the Python implementation of this formula, like how to solve this integral. Again, you don't need to go into the details of the code, just try to understand this. So this is a function that integrates the distribution function in a given range. So the important thing is to look at the results. Okay, so what I am doing is, I'll tell. So I have picked any random normal distribution. I have chosen a mean. You can pretty much choose any value as your mean, and I have chosen a standard deviation. The so I am integrating this normal distribution and check like what I get. So you can see the results here. The first result tells you the probability that your data will lie in one standard deviation from mean. So what does this lies within one standard deviation from mean says? It says that okay, this is your normal distribution, So what is the chance that your data will lie in this red region? That is one standard deviation from the mean. Similarly, we can look at the probability in within two standard deviations, that is the sum total of this blue and red regions. Similarly, within three standard deviations, that is blue, red and green regions combined. So we'll have a quick look at the results. So within one standard deviation, the probability is 0.683 or 68.3%. Within two standard deviations, 95.4, and three standard deviations is 99.7. And outside three standard deviation is 0.003. So there is 0.3% chance that data will be in this region, in this part and in this part, and that is the beauty of normal distribution. So again, if I go back to that player example, your mean is 10 and your standard deviation is 2. You multiply your standard deviation by 3, so 2 into 3 is 6. You subtract and add it to the mean, so 10 minus 6 is 4 and 10 plus 6 is 16. So there is 99.7% chance that your data will be in this range from 4 to 16, and anything out of this range you can pretty much consider it as an outlier. Although it depends on data, but there is a high chance that it will be an outlier. And so okay, the fifth result. So mathematically also what it gives, I have checked the probability at a single point. So basically both the values I have given as the same, and you can see that the result is 0, because now it's a bit more easier to understand, because area is obviously in a 2D plane, and at a single point you have no area. A single point cannot cover any area, and for normal distribution probability is the area. So that is the reason that a probability at a point is always 0, because it is not covering any area on the graph. So it's a bit more playing with the integration, like probability that x lies in the first half. So by first half, I mean this region to the left of this, left of mu. So you can see that as the graph is pretty much symmetric, so it should be 50% here and 50% here. So first half 50%, second half 50%, and area under the curve is 1.0. Now there are two important points that we need to consider is effect of mean on the shape of a curve. So how does mean affect the shape of Gaussian distribution? So instead of understanding it from a theoretical point of view, it's easier to visualize it on the graph. So what I have done is I have generated three normal distributions from a Python. They all have the same standard deviation, that is 0 0.5, 0 0.5, and 0.5, but the mean is different, 80, 100, and 120. And the result looks something like this. So basically, you can see that the graph shifts according to the mean. Since the graphs are randomly generated, so they are not perfectly symmetrical, but you can see that they all are having similar shape. And as we earlier discussed, the peak of the graph is right above the mean. So the graph with the mean 80 would be appearing a bit earlier than these two. It's having mean 100 and it's having mean 120. So if you are not changing standard deviation and if you are only changing the mean, so graph will translate in horizontal direction, but the shape won't change. Now we'll have a look at standard deviation, the effect of standard deviation on the shape of the graph. So again, a distribution, three distribution with the same mean 100, 100, and 100, but standard deviation I am varying this time. It's zero point 0.5, sorry, it's 5, 10, and 20. So now you get to see some interesting stuff. So you can see that with change in standard deviation, the graph flattens or contracts, and it has a direct effect on the shape. And why it has, because if we go back to the earlier graph, we can see that this gap, this red gap right there, is 2 times standard deviation. So what it does is it basically it determines the stretch or the expand of the graph. So the same results that we get here. So this blue graph, it has a standard deviation of 5. So standard deviation of 5 means the graph will have a lower stretch. That is why the total region is very low. But if you look at the green curve, it's having standard deviation of 20. That is 4 times to the blue one. So you can see that it is far more stretched and far more flattened out. So that is how the Gaussian distribution varies with the mean and with the standard deviation. So here are some important points about normal distribution. So the curve is symmetrical as we have looked at it earlier on about the mean, and maximum values are will be accumulated towards the mean. And it's a very important rule, that 68, 95, 99.7 rule that I have also talked about. It's the same thing, that 60, if you know that your data follows a normal distribution, so you can expect around 68.2% of points to be lying within one standard deviation, and so on. It's the same thing, one standard deviation, two standard deviation, and three standard deviation. And you can check it here as well. Most of the data is close to the mean. So okay, we'll move ahead, and it's a nice topic that is related to this Gaussian distribution, that is skewness. So what skewness is, in simple terms, it is a measure of asymmetry of probability distribution. So as you can remember from the earlier figure, this is your standard normal distribution, a nice bell-shaped symmetric curve. But a lot of times in real world, if you try to plot your data, it may not follow this standard normal distribution, but it can be a slightly bit more asymmetric. So this asymmetry can be measured by skewness. So there are two types of skewness, positively skewed or right tailed. So if your data distribution is a tailing towards, so this elongated part of the graph is known as the tail. So if it's tailing towards this right side, so it's positively skewed. It's said to be positively skewed. And if it's tailing towards left, it's said to be negatively skewed. And as you can see that in the earlier webinar, we have a look at the three most important measures of central tendency, that are mean, median, and mode. So for a symmetric distribution, they all three are equal. But if the distribution is asymmetric, then these three are unequal, and your mean is bound to move towards the direction of the tail. So why skewness is important? Because first of all, it indicates whether the deviations from mean are positive or negative. Second, the confidence intervals from standard procedures will fail. So what confidence intervals are, we'll have a look at it in a short interval of time. But the standard testing procedures and the standard confidence intervals that are very important in data science and machine learning results, they all will fail if your data is highly skewed, because you can see that mean, median, and mode are no longer equal. They all are different. So we'll keep moving ahead, and we'll see confidence intervals later. So we'll come to the most important topic, especially in hypothesis testing. And this obviously we'll have a look at hypothesis testing in a lot more detail in the next webinar. So what sampling is. So before defining sampling, we'll first have a look at two important concepts, that is population and a sample. So what is a population? Population is group of all objects that are under study. It's called a population or a universe, and it can be finite or infinite. Like if I have to consider an example, say we are studying about the scores of a particular footballer. So scores of that footballer across all the matches of his career are the population. Or say you are studying the average income of people of India. So average income of each and every person of India is your population. The data of each and every individual or object is your population. And what is a sample? A sample is a finite subset of population. So say you pick a small region of India and you study the people there. So that is a sample, because you are not studying the entire population. Now comes the most important question, that is, why do we need a sample? So there are two reasons why do we need a sample. First is complete enumeration of population is not possible, because in maximum cases you just cannot gather the data for entire population. And it's pretty obvious that if you want to study something on population of a country or something, so you cannot just go to every person in the world or in that country and ask them question about their income or their height or their weight. So there is no way possible, like only in a rare case you can study a complete population, but in most of the cases study of complete population is not possible. And second, inspection is often destructive. Like, if I have to pick an example, okay, say you are testing electric bulbs. So there is a nice electric bulb or tube light manufacturer, and you are studying like whether they meet up to the standards that are being put up by the international regulation bodies or not. So if you try to like test an electric bulb, like what is its life and for how long it moves, so obviously you will have to light that bulb. Or say you are inspecting crackers. So the way to inspect them is to burn them. Or say you are testing fabrics, like how strong or how weak a fabric is. So test of strength can be carried out only after tearing or like destroying that fabric. So you cannot just destroy all the population, because what do people will sell then? So these two are reasons that you cannot gather data about the entire population. So the population is generally always unknown. So what we have to do is, we can only study a sample, we can only gather the data about a sample, and we can only study that sample, and we can see like how the population behaves based on the data from the sample, and this is known as inferential statistics. So a very important thing to take care about sampling is type of sampling, which depends on the task at hand. So there is purposive sampling, and in which the samples are selected with a definite purpose in mind. So the drawback is that it suffers from favoritism, because you are bound to select units in your sample that you tend to favor. Then there's random sampling. Then there is random sampling, where the units are selected at random. And in almost all machine learning and data science tasks, this one is generally supposed to be the best form of sampling, because every object has an equal part of being selected into the sample. And there is a stratified sampling, where you select according to separate stratums, and it is a true representative. If I have to put it in an example, say you have different religion ethnicities in a region. So basically what you will do is, you'll pick up all the regions, or pick up say all the religions, say Hindu, Muslim, Christians and everyone, and you will you will define a proportion, and you'll pick sample from each of the regions separately. So you are not randomly sampling, you are sampling from all the different regions. So that is stratified sampling. But we'll generally focus more on random sampling, because this is found to work very well in machine learning and other tasks. So it's a demo of the sampling of the data. So here I have a data from of a cotton yarn produced by a spinning mill. It's a count data. Count basically in a you can basically consider count as the strength of a yarn. So there is a spinning mill that is producing a cotton yarn, and we are studying the count of the yarn. So the data we have is strength of 10,000 yarns. And now we need to sample from this. So there are two functions, that is numpy random.choice and random.sample, which you can use to pretty much sample the data from. So I'm using numpy.random.choice, and I am generating a sample of 50. So basically in real life scenarios, you have only this. You have a sample, you don't have the entire 10,000 spindle data. So based on this, you need to estimate the population. And this is what sampling distribution and hypothesis testing, the topics that we are going to cover today and in the next webinar, are all about. So you have a sample, it may not be of size 50, it may be of size 1000, but you definitely do not have the entire population. And based on this sample, you are going to analyze the entire population, because at our best we can just collect a sample, we cannot collect the entire population. So this is how we can sample in Python using both these functions. So now comes a very central concept in sampling distribution and statistics, that is center limit theorem. So first we'll have a look at what a sampling distribution is. So frequency distribution of a sample statistics over many samples of a fixed size is a sampling distribution. So earlier we had a look at probability distribution or data distribution. So what data distribution does is it tells you how the data is distributed or what is the probability of your data. But a sampling distribution is a different thing. What a sampling distribution tells you is that what you actually do is, say you have a population, you pick samples from that. So if I go back to this example, so this 10,000 numbers strength data is my population. I pick different samples. So this is one sample of size 50, then I pick another sample of size 50, then I pick a third sample of size 50. Similarly, I keep on picking different samples from this, and I calculate a mean of them all. I can calculate mean, standard deviation, pretty much everything. So for our example, we'll calculate mean. So I calculate mean. So say I pick 100 samples. So I'll have 100 different samples and 100 different mean. So when I plot this data of mean, now I'm not plotting this original data, I'm plotting the mean of the samples, then I'll get a sampling distribution. So basically how your sample means are distributed. So what central limit theorem tells is that the sampling distribution of a sample means approaches a normal distribution as the sample size tends to be larger. So what is exactly going on is, you have a population distribution, you have these points, say again we'll come back to this cotton example. So you have this 10,000 cotton data, you have plotted them all on the x-axis and counted their frequency. So say we got a graph like this, it can be any randomly graph, it can be binomial, it can be Poisson or any unknown distribution. So the mean of our population data is mu and standard deviation is sigma. Now what we do is we fix a sample size n. It can be 50, 100, 10, pretty much any value. So we generate a sample of size n and calculates its mean. Then we again pick a sample, calculate mean, again pick a sample, calculate mean, and we go on doing this. So now if we plot the data of this mean, so every time we'll get a Gaussian distribution. This is what central limit theorem says, that your probability distribution could be of any shape, but the sample distribution will be always a Gaussian distribution, given that the sample size you pick is large. And by large, I mean good experimental value is 30. So if your sample size is larger than 30, so your sampling distribution of mean will always be a Gaussian distribution, and the mean of this is same as population distribution, that is mu, and the standard deviation is sigma by root n. So the standard deviation of population divided by square root of the sample size that you have picked. And this is very, very important, as it is the basis of entire large sample testing, which we'll have a detailed look in the next webinar. So why is it useful? We have already discussed that it forms the basis of large sample testing. And as a general rule of thumb, the value you should remember is that a sample size of greater than and equal to 30 is considered a large sample. So if you are keeping your sample size to be larger than 30, so it is considered a large sample, and the sampling distribution of such a sample will be Gaussian. So now we'll have a Pythonic implementation of this so that you can visualize whether it works on any random generated data or not. So this is a function that I have written. What it does is it generates simulated die rolls. It generates 1,000 die rolls of 10 dice. So what we'll do is, if when I'll run the code, okay, yes. So what it does is it takes different samples from this, and it will, like, first case, it will sample one die roll. That is, one means one die roll at a time. 20 means 20 rolls at a time are sampled, and we are calculating their mean. So we are generating 1,000 die rolls, and we are sampling with a different sample size, and we are calculating their mean, and we are plotting the mean. So if we see the results, so when we have sampled with the sample size of 1, so you can see that obviously because we have different samples, so they will result in different means, and the data is pretty much distributed everywhere. We have mean 1, 2, 3, and all the values. But as you can see, as the sample size increase, this is 1, this is 20, 40, 80, 100, 200, 1,000 and 10,000. So when the sample size in it is 10,000, so you can see that the distribution moves, looks a bit more like the Gaussian distribution. And this is what our central limit theorem says, that as the sample size keeps on increasing, the sampling distribution is approaches normal distribution. Just to be a bit more clear, what we are doing here is we are generating die rolls, and we are picking number of samples from them. So say if your sample size is 10, you are generating different die rolls, and you are picking different set of 10 dies, and you are calculating their mean, and you are plotting that mean. So this is what we are doing, and we see that as the sample size increases, our distribution looks to be more and more normal. So these are the observations, and it pretty much talks about that as it will increase the sample size, the distribution looks normal. And one important thing you can notice is that the range of x-axis values, in the first graph you can see that x-axis values ranges from 1 to 6, then 2.5 to 4.5, and in last one it's 3.4 to 3.5. So all the means are in this range, and it's an interesting result, because when we talk about probability, the expected or mean value of a die roll is 3.5. So you can see that as the sample size increases, the mean of sample is getting more and more closer to the population mean, that is 3.5. And that is what central limit theorem says, that if I go back, the mean of population distribution is mu. For a die roll it's 3.5 theoretically, and sampling distribution it's also mu. So you can see that for samples, for a larger sample size, the values are getting pretty much closer to the expected theoretical value of 3.5. So this proves our central limit theorem. Next, this what I was talking about. That this is the way, I won't go into details. This is the way how to theoretically calculate the mean for a die roll, and you can see that this value is 3.5. So this is a theoretically expected value. So law of large numbers. A law of large number is also an important theorem that is pretty much related to central limit theorem. And what it says that as the sample size grows, the sample mean gets closer to the population mean. And it's pretty much, it makes sense because we all always like observe it in our daily life. So we'll see its simulation, and then we can better understand like what's going on. So what we are doing is, you can see the results here. I have rolled a dice and I got a number 3. Okay, it's obvious we can get any number from 1 to 6. Then we roll 10 dice and we calculated average. So on rolling 10 dice, we'll get 10 numbers. So when we average, we get the result 4. On rolling say 500 dice, so we got 500 numbers, we averaged them and we get a value 3.47. We rolled 15,000 dice, average 3.508, 50,000 average 3.504. So what it's saying is that as you increase the sample size, the average is getting closer and closer to the expected value, that is population mean. And we have also already talked about it, that the expected value for a die roll is 3.5. So you can see that this is the orange horizontal line is my theoretical value, and this blue line is different number of samples. So you can see that as the sample size increases, this graph wiggles a bit, but on higher sample size, you can see that the wiggling is gone and the graph is converging to this value. So this is what this law of large number says. And it's pretty obvious that as you get more and more numbers in, say in a first roll you may get a 6 or a 1, but as you roll more or more dice, you can get pretty much all the numbers, and then the mean would starting to look like a bit 3.5. So okay, this is what the graph is telling us. And now I think I'll stop for a moment for Q&A so that we can address the questions if people have any, and I'll hand over to Sneha.
Yeah, thank you. Rishika, do you want to take over?
Yeah. So if anyone has any questions, feel free to drop them in the Q&A box. I don't see any ones currently open, but feel free to drop any questions you have. We can try to answer a couple.
Okay. So the other thing, one of the questions that I found interesting is about outliers, like how is outliers affecting the central limit theorem and statistical analysis. So as you know from the first webinar that usually outliers affect the mean the most and very little effect on the median and mode. So it is important that before you do statistical analysis that you remove the outliers or handle them in the appropriate ways that we discussed in the first webinar before doing your statistical analysis. So that's how you make sure that your statistical analysis stays significant without any noise or less noise as possible. Yeah, that's one question I found interesting. The other question that I found interesting is someone asked if we could do a side-by-side comparison of the distributions. Unfortunately, we don't have it here, but you can make sure. I mean, we actually just opened a Medium page for Women Who Code Data Science track. So we definitely will write a blog post answering that question, showing the difference between normal, binomial, and poisson distribution.
And yeah, and one more thing, adding to question, like the key difference between the binomial and Poisson distribution, the basically main difference we can put from it, like the binomial distribution is like there are number of trial like, are repeated, while the in probability distribution they are independent event, like and like they are not they are not fixed number of attempts, like in binomial distribution there are unlimited number of trials. And also we can put a blog or post on the human code.
Yes, thank you, Aryan. We are expecting to answer.
And yeah, and also there was one more question, like the that the mean has a larger sample bet and the better we can have the better model. Yes, like Rishika has answered, we can get closer to the normal distribution on all. And also the there are specific advantages of the larger sample size, like if we have larger sample size we can have have the various effects on this the mean value and outliers. And also there were and if you have small samples, we have to more do the iterations. And yeah, and there are also like we have a small data set, so there we can basically we have to do the larger number of iterations in the smaller data set.
Sounds good. Thank you. Ravi, if you're back, I do have a question for you on the notebook. Okay, we'll give Ravi 2 more minutes.
Yes, Neha, I'm here. Yes.
Okay, awesome. So Ravi, there was this question in the initial binomial distribution, the coin toss. If you go to
Yes.
the top. So there was this question that the toss results is not defined before. So in this thing, do you think there is a missing code here?
I actually didn't get like what is not defined.
Toss results, toss underscore results.
Okay. Maybe I missed that.
So yeah,
Okay,
the one,
I'll correct that after.
yeah, the one
Maybe
thing
I
we will
missed that
do
part.
is,
Yes.
yeah, we'll fix it and we will upload the
Yes.
new code as soon as possible after this.
Yes.
Yeah, but otherwise, wonderful presentation. Thank you, Ravi, and you can take over from
Okay.
here.
Sneha, just I want to ask one thing. How much time do we have left?
Oh, it would be nice if you could wrap it up in the next 20 to 25 minutes.
Okay, I'll try my best. Okay.
Thank you.
So I think I can start again now.
Yes, you can start again.
Yes.
And the toss results, for everyone who thought toss results were not defined, we will update the code and share it with you all through the Slack
Yes.
channel. So make sure you join our Slack channels. Thank you.
Yes. So our next topic is confidence intervals. So what confidence interval is? So what we are doing is right till now we have understood that it would be ideal if we can have the population data, but we cannot have a data for the population. And what we can do at our best is we can generate a sample, or we can have find the data for the sample, and based on that we can try to estimate the data for the population. So say we are trying to find the population mean, say for anything like, okay, height of people living in India, or height of say males living in India. So we cannot go to every individual and measure their height. What we can do is we can measure say 10,000 or 50,000 people, and based on that we can estimate like what the average height should look like. So this is what we are doing in sampling. So it's obvious that the sample mean that we'll find, it won't be exactly equal to the population mean. So there will always be some uncertainty, and the confidence intervals are the way to measure that uncertainty, so that we are not like on the wrong side of the results. So there are various ways to calculate confidence intervals, and one of the ways that I am using here is based on large sample testing. That is when your sample size is greater than 30. Since every time in machine learning and deep learning data science we talk of large data set, and we always want to get large, really large and nice data set. So every time almost our sample size would be comfortably more than 30, so we can use this formulas. So this is our confidence interval formula, and we'll have a look at what it does is. So again, what we are doing is I am taking that count data again, and now this time I'm generating a sample from it, and based on the sample we'll try to estimate the mean of the entire data of 10,000 values. So for now, since this is ideal world, we have the population and I can calculate the population, but it is not available in the real world. So in the ideal world, this is my population, that is mean of all the values. So okay, now what I have done is I have decided a sample size of 100 and a confidence value is of 0.95. So when you talk about confidence intervals, you need to define a confidence value, like how much confidence you want in your results. So based on the code, what we get is the sample mean is 25.15, and the confidence interval is this 24.58 to 25.712. So in simple words, what a confidence interval says is that based on this sample, there is a 95% chance. The 95% is the confidence level that I have chosen. You can pretty much choose any value, any level, except obviously 100%. You cannot choose 100%. But apart from that, you can choose any value. So based on this sample of size 100, there is a 95% chance that the population mean would be in this range. It would be between 24.58 to 25.72. This is the basic like crux of what a confidence interval does. So there are various ways this code is like I have implemented it from scratch, but you can also use SciPy generated functions. So then also give you the same values. There is a bit of difference in values, and that is due to first of all these results are random. The sample may not be same, and second the value of that is being used. So it it may have been somewhat different accuracy. So that is why the results are a bit different. So it's again the same thing. What does confidence interval actually tells us? So it says that there is 95% or 99%, whatever value you have chosen for the confidence interval, is chance that the population mean will lie in this range based on the sample data. So what we are doing, we are estimating population data from sample, and since we cannot give an exact value because we don't have the complete population, we gave an approximately range that this is the range that is likely to contain the population data, because we without measuring the population in its entirety, we cannot give a single definite value. So there are some important points. Effect of sample size. So based on this value, you can see that as sample size will increase, our confidence will increase and our confidence intervals will go down. So here is quick implementation. So in the first case, the sample size that I have taken is 100, and you can see that for the same data, it's the same data. The confidence interval is this one, and the length of interval, that simply means the difference of these values is 1.14. And at a sample size of 5,000, the difference is 0.16. So what it's doing is, because we have already talked about law of large numbers, what it says is that as sample size increases, your sample mean will be closer to population mean. So in a larger sample, our sample mean will be closer to the entire population mean. So that is why our confidence interval is narrower, and we are pretty sure that population mean will be in this range. So a narrower confidence interval means that we are highly confident about our predictions that it will be in this range. So you can see that you are almost exactly equal to the exact population mean. So as you will increase the sample size, you'll get more and more confidence in the predictions. But here is the catch, because a lot of times sampling and testing is costly. You have to find the data, you have to do surveys, you have to test object. So cost and time are involved. So you cannot every time have very high sample size. So it's a trade-off. You need to balance the accuracy of the estimate and the sample size. Now comes the effect of confidence level. So this Z is your level of confidence that you are defining. So same data, same sample size. I'm not changing the sample size. First, the case is that confidence level is 90. It's my mistake. It should be 95. Okay. So first I am doing it at a level, at a confidence level of 90, and you can see that the gap of this interval is 0.95. At a confidence of 99, so at a confidence of 99, you can see that the gap has increased. Now a lot of people get confused that with greater confidence the interval should shrink, but it's actually wrong. It should expand, because what this means is that there is a 19 that we are 99% confident that population mean will be in this range. So in order to get more confidence, we will have to expand our interval so that population mean will be in this region. So as you increase the confidence level, your confidence will obviously increase, but your level or your interval will get expanded. So this is an important point that we should keep in mind. So our next topic is standard error. So what standard error is? Simply put, standard error is the standard deviation of sampling distribution. So if I go to that graph again, so this is our population distribution of mean, mu, and standard deviation sigma. We draw samples of size n. So if the sample size is large enough, our central limit theorem says that we'll end up with a Gaussian distribution with mean mu and standard deviation will be sigma by root n. So the standard deviation of this sampling distribution is known as the standard error. That is the value sigma by square root of your sample size. So why it is important? Because it forms the basis of theory of testing that we'll have a look at later. And it actually tells you the difference between this. So basically what we have seen that we don't have the population, we only have the sample, and sample data may not be exactly equal to the population. So what is the difference between them? Is if whether the difference is too high or too low, it's determined by this standard error. And also it gives a measure of reliability. So reciprocal of standard error gives a reliability of your estimate. And also it helps to estimate the confidence interval. So it is a pretty useful value. And this is the implementation. It's a very simple formula. So you can see that again from that cotton data, I have generated a sample of size 100 and confidence level 95. So you can see that this is our length of confidence interval 1.14 and at sample size of 400. Okay, so this is my standard error and this is my reliability, which I have calculated from standard error. So reliability is 3.43. Now I have kept everything same. I have just increased the sample size. So you can see that the reliability has increased. It has doubled. So this is how standard error is important. The standard error was zero point 0.2 earlier. It's now 0.146. So standard error has gone down with increase in sample size, but our reliability has increased. So this is why it's an important thing to look at. Our next topic is the bootstrap method. Now, what bootstrap method is? It's again one of the methods to draw inferences about the population. But what makes it different is that it's a non-parametric method. By non-parametric method, I mean that it does not assume any distribution for the data, and it's practically very useful in machine learning and deep learning because other methods, the one that we used earlier, this formula for confidence intervals, this you can only use when you know that your data follows a normal distribution. But if you don't have any information about your distribution, you can use bootstrap method. Here you do not need to assume any distribution. So we'll see how it works. So basically what we do is we create simulated samples from our data by resampling with replacement and form our sampling distribution of our own. So the only difference is earlier we were assuming our sampling distribution to be Gaussian and we were using mathematical formulas. Now we are creating our own sampling distribution and then we are calculating the confidence intervals. So this is a Python implementation on a Hertz data where you have data about patients and based on that you can predict whether a person has a chance of getting a heart attack or not. So this the more information on dataset can be found here. So what basically we are doing is, so since it's a classification problem, we'll have a look at classification in data webinars. So I have deliberately kept this example related to machine learning, so it will be a bit more easier to relate. So what we are doing is we are fitting a decision tree classifier on this data to predict whether the person will get heart attack or not. And we are calculating the accuracy of our classifier and also the confidence interval on that accuracy. So basically what we do is this is our data. we fix a sample size and a number of iterations. So what we do is every time we sample from this data, so we'll pick some of the rows, not the entire data. We'll fit a decision tree classifier on them. We'll calculate its accuracy. So I am repeating this procedure for 1,000 times. So 1,000 different samples from the same data, 1,000 classifiers, 1,000 accuracies. And then I'm plotting the distribution. So this is the plot of that accuracy. So it's total 1,000 accuracies. And so this is what bootstrap method does. You take your data, you sample it 1,000 times or 10,000 times, whatever you like, and every time you fit a model, you calculate its accuracy. So now you have generated your own sampling distribution without any knowledge of the original distribution. So now based on this, you can calculate your confidence intervals. That is what we have done here. So based on the percentiles values, we have calculated our confidence interval, and this you can see that this is our confidence interval. This is the mean of accuracy of 1,000 classifiers, and this is our confidence interval. So it's good to not only report a single number, it's always good to report a confidence interval. So that with 95, because you can see that every algorithm has a bit of randomness to it, and also you cannot expect that you have all the data in the world. So that is why it's better not to report a single number. So it basically it gets you on a bit more safer side uh, in estimating your model performance, that you are 95% sure that your accuracy should be somewhere in this range. So it's a better way to report your results. So it's practically very useful method, this bootstrapping method. So now next we'll have a look at some of sampling distributions that are commonly used in statistical testing and statistical experiments. The first and most useful of them is student state distribution. So what is this? Student state distribution is almost a lot similar like the normal distribution, but the only distribution is that it's specifically designed for smaller samples. Like earlier we talked about center limit theorem, that if the sample size is large, that is greater than 30, so everything converges to a normal distribution. So you can use normal testing and the formulas that we have looked at earlier. But what if your sample size is smaller, say it's 5 or 10, then you cannot use Gaussian distribution. And in this case, you will have to switch to student state distribution. So I won't go into the details of this because we'll have a look at it in the next webinars, like how different distributions are used and what are the differences. So the main key takeaway is that it's to be used when your sample size is small and particularly less than 30. Then you cannot use normal distribution. So this is how the graph of it looks like. It's Python generated graph, and it does not have any particular shape. Like based on data, it will keep on changing its shape. And this is function that I have written so that if people are interested, they can play with it. So what it does, just like we found area on normal distribution, this finds area on probability distribution. So this this dangerous looking function right there is the probability distribution function. So like for data scientists and machine learning, you do not need to remember this function, like what is this gamma function and everything, but you need to know the t statistic that we'll have a look in the next webinar and why it is used. This formula, if you want, you can pretty much forget it. So if you want to have a look at it, this is the code on how to integrate it, but it's not something that you should remember. If you are interested, you can have a look at it, but it's not important. It's not that much important to remember. So next is long tail distribution. So unfortunately for this, I don't have any Python implementation. So the basic concept is that, as you can remember, all the other distributions, they have tail on both sides, but the tail is it's not it quickly goes down to zero. But long tail distribution, it has as the name suggests, it takes a lot of time to tail to zero, as you can see in this graph. So there is no need to go into mathematical details, but the main key takeaway is that the tail takes a longer time to go to value zero. And it's very why we are studying this, because it has a lot of application in sales and finance and some of other domains where there are a large number of items that have very low number of sales. So you can see that this value is very low. So we can model the sales data using this distribution. So that is why this is important. So next we'll move on to our next distribution, that is chi-square distribution. So what a chi-square distribution is, um, in short terms, what a chi-square is, it's the square of your standard normal distribution. So if you have a bunch of normal distributed variables, you can square them all and sum them all, then you get a chi-square distribution. So instead of going into the theory, I think it's better to understand it from an example. So this is how the graph looks like. So based on different parameters, it can have different shapes. There is no fixed shape for chi-square distribution as well. So only Gaussian distribution that we have seen far has a definite shape. All other distributions, they do not have a definite shape. So okay, so why it's used? So chi-square has an important use, that is goodness of fit test. So we'll understand what a goodness of fit test is. So we are using this data. Okay, so this is our data. It has several columns. Say we are interested in two columns, that is sex or gender and smoker. So whether that person is a smoker or not. So we have picked the data, and this is our interested data in nutshell. So there are 60 males that are smoker, 97 males that are not, 33 females that are smoker, and uh, 54 females that are non-smokers. So what goodness of fit test allows us to do? So basically, based on this, we can check whether two variables are related to or not, or whether they are associated or not. Say you want to test whether like gender does have an effect on smoking habits or not, or whether both males and females are equally likely to smoke. Because based on this data, you cannot tell what's the exact scenario, because it's a very small data set. You do not have data set of all the population of any country or something. So we'll have to test it statistically. So this is your goodness of independence of attribute test. It allows you to test whether two variables are related or not. So in Python, there is a nice function in SciPy library where you can calculate this expected frequency. I will go into the details in the next webinar, like how the formula works. This is the formula. So based on these values, you can quickly calculate what's this. So this is the value that you are looking for, this chi-square statistic, the one that is shown here, this chi-square. And based on this, you decide whether the difference is significant or not. So basically you are comparing these values. These are the values that you have got from your data, the observed values, and these are the values that you have generated from the formula, which basically signifies that no, there is no difference among the gender. So when you compare both the values, this is the result, that there is no relationship between the variables and they are found to be independent. So basically you can say that no, like from this data, you cannot say that gender has an effect on smoking abilities or not. So this is how you can calculate association between two variables using the chi-square test. Next is F-test. So F-test is a group of tests that basically lets you compare variance of two samples of or two populations. Till now, using Z-test and using T-test, again, you'll have a look at it in detail in the next webinar. So you were comparing mean of the data, like whether sample mean and population mean or two population, they have same mean or not. But what if you need to compare variance of data? So then you will use this F-test. So simple, it's very simple to calculate. You have both your data, you calculate their variance, and you divide by them, and then based on some predefined values, you can check whether they both have the equal variance or not. So these are the general steps for an F test. We won't go into detail. So this is the implementation. We have randomly generated two data, X and Y. We have calculated their standard deviation and their variance, and we have divided them like as you see S1 square by S2 square. And based on p value and statistics, you can see that we have rejected the null hypothesis. We'll see all the things in detail in the next webinar. So in on this data, we have sufficient evidence to say that population variances are not equal. So the key takeaway is that it makes you compare variance of two population, unlike the mean that we were comparing till now. So next we'll move on to the next topic, that is bias. So it when we'll talk about sampling, and every time we do sampling, bias will be always be there. It's unintentional, and we all know that we do not want it. And the two prominent types of bias are selection bias or sample bias. Selection bias is when your selection is in such a way that proper randomization is not achieved. Because I have also talked earlier that in machine learning and in data science, random samples are known to work well. But what if, say, due to some reason, proper randomization is not achieved? So you will suffer from selection bias, and it can be considered as errors in the process after sample is gathered. Say you have generated a sample, and then the process you carried out has led introduced some bias. But very sample bias is that when your sample itself is biased, or your way of generating the sample is not right. So why bias is important? Because it's a big concern in AI. There have been a lot of incidents where the AI algorithms has found to be biased regarding color or gender. And why it happens? Because they learn from data, and data can be biased. And why we are worried about bias is because if your sample is biased, then the results or the accuracies that you will get, they can be misleading, and you cannot trust your results. So that is why addressing bias is a big concern, and it's a very hot research topic currently in AI. And last, we'll get to one last topic, that is regression to the mean. So first, we will talk about what a bivariate distribution is. So it's a series of terms where we have two values associated with each unit. So earlier, all the analysis that we have done, it was univariate distribution. So for each point, you have a single data like height of the person or income of the person. But bivariate distribution, where you are studying two parameters about a person, say height and weight and age, or something like that. So what regression means is, the term regression literally means stepping back towards the average. So what it actually means is that, okay, I think it's better to understand it like this. So as we see in sports, whether it any sports, it's football or it's cricket or it's any sport, if a person is playing well in 2 or 3 matches, then in the next matches, there is a high chance that he or she won't perform that well. And if a person is going through a lean patch in 2, 3, 5 matches, then in the next matches they won't score that. There is a high chance that they will perform better. So that is actually regression to the mean. Because, or you can say that law of averages. So in the long run, the results will always average out. So if you are bad for a time, you'll get to better, and if you are doing good, then average, so your results are going to dip. This is what regression to the mean actually mean in real life. So next we have a quick Pythonic implementation again with the die rule. So you can see that this is a single die rule. So a single time you throw a die, you get a number 5, and you can remember that the average should be 3.5. Now I have generated 6 rows. So you can see that the numbers are 1, 2, 5, and 6. So there are numbers like that. I have got 2 times 6, 2 times 5, 1 times, and 1 times. So as I keep on increasing the number of rows, you can see what's happening. that the number of occurrences of every number is almost the same. So this is what regression to the mean, that for a single roll, you can get 6, 5 or something like that. But as you will keep on rolling and rolling and rolling again, you will get all the results with the equal probability, because we know that on a die, every number has an equal chance of getting. So out of 6,000, you can see that almost all are close to this 11,000. So this is regression to the mean. Your results will always go towards the mean in the longer run. So this is pretty much it. So now we'll go to our conclusion. So statistics and pattern recognition is a very important part of AI and data science. Data sampling and statistical experiments are a part of data science jobs. That is why a lot of statisticians get into data science and they get very good jobs. Understanding the distribution of data helps in discovering the underlying patterns. Population data is almost always unknown. Much of the information can be inferred from samples, and that is why we care so much about this testing and sampling, because population we cannot know. And when the distribution is unknown, bootstrap confidence intervals can be used to estimate. So bootstrap is a very useful method, especially for us. And at last, there is a bit of optional content. So it's a script. I'd suggest don't go into coding details because it's a bit too much. But what it does is it's a nice function where you can pretty much choose any Gaussian distribution. So what you have to do is just pick a mean here, just pick a sigma here, and obviously your standard deviation should be less than your mean. And you can pick any two values here, this one, A and B, and it will plot the area between these two graphs. So you can see that I have chosen mean and sigma 5 and 1, and these two values I have chosen. So it will plot you everything that you need to understand, like how probability on a normal distribution works. So you can change these values and you can generate this graph and this formula as well on how the probability is working. So that's pretty much it. That ends the webinar, and I'll hand over to Sneha. Sneha, are you there?
Hi, yes, Rishika, can you conclude the session, please?
Yeah, let me just pull the slides up.
Yes. Ravi, if you would like to end the session, please.
Yes, actually, sorry, I didn't hear you.
Can you end the presentation
Okay,
so that
yes,
Rishika?
just doing, yes.
Yes.
Okay. Let's see, can everyone see that?
Yes.
Okay, so yeah, thank you, Ravi, for today's session. I hope everyone was able to have their questions answered. There were some really wonderful questions today. And so to carry on for next week, we'll be focusing on statistical experiments and significance testing. So the topics to be covered are why are we looking at statistical experiments, variability in estimates, hypothesis testing, additional evidence, and then A/B testing. So that'll be a week from today, same time, same Zoom link. So once you've registered for the first webinar, it is the same consistent link for all the future sessions. That'll be presented by Angela, who is a data science manager at Medtronic. And here are some wonderful member benefits of being part of WWCode data science. So you get coding resources, tutorials, articles, videos, and other educational materials to excel, whether you're trying to learn a new language, learn a new topic, whatever it might be. You can also find leadership opportunities that expand your skills and also enhance your career. So I myself am a lead for this track, and I've taken a lot of value from being in a position like this. So that's definitely something to look forward to. We are a global community, so you can advance your technical skills with other engineers at our nearly 2,000 events annually. We also have a job board that's posted and it's updated quite frequently, so you can pursue your next step with any companies that you're interested in. We also offer scholarships and free tickets, so you can benefit from the $1 million in conference tickets and scholarships that are awarded annually. And also we have this wonderful feature called Applaud Her, where we give and receive recognition for the different achievements from both industry peers and leaders. So, if someone presents in a webinar like today, like Ravi, we would applaud them, anyone who's organizing a series, anything like that. So we're a very wonderful community. We like to collaborate, we like to support each other. So if you are a member of this online track, it would be wonderful to get all of these benefits and more. And I believe there's been some links shared in the chat by, let me just make sure those were shared. But yeah, just to our different social media accounts and some of the links that were shared just here on this slide. And that's it for today. Thank you so much for everyone for joining. I hope I took a lot from today's session. Thank you again to Ravi. It was a wonderful session. And yeah, thank you everyone. I hope you have a wonderful rest of your day. And as always, this session is being recorded and the recording will be made available on our YouTube channel and also will be posted to Slack. So make sure that you're part of our Slack community as well. And that'll be it. Thank you so much.